This will be video number 2 on special applications of integration. And what the remaining videos out of the series will help us investigate is the ability to use calculus in three-dimensional modeling. And our goal here is to calculate the volume created by revolving a bounded region around an axis. And here's our problem for this video. We're going to look at a curve defining the top half of a spherical ball that can be modeled by the function f of x on this interval from a to b. The ball is formed by revolving this region around the x-axis. And what I mean by that is this region bounded here between the curve and the x-axis itself. And what we're going to do is write an expression to model the volume of the ball. And this may seem like a somewhat strange problem because we're very well acclimated to dealing with areas of 2D shapes, and so how can we apply knowledge about 2D scenarios to three-dimensional scenarios? Well, how we're going to do that is to break this down and turn it into a two-dimensional scenario. And so instead of trying to revolve that entire region, trying to think of how to use this area that I've colored in to make a 3D image, what I'm going to take a look at is one small piece of this region. And what I'm going to use, and this is a term I'll use going forward as well, is what's known as a representative rectangle. And so instead of trying to revolve the whole region around, I'm just going to take a look at one little tiny space of this region and revolve that around the x-axis. And what I mean by that is imagine holding out a rope and swinging that rope. And think about the arc that you'd create. This rectangle, if I were to revolve around the x-axis, would swing around and come back to the top. And it would trace through this entire space right here. And what I'm going to do is take this region that I've traced out and just move it over here. That rectangle, or again, go with the example of the rope, it's not changing length. So when I swing it around, what I'm tracing out is really just a circle. But a little bit more than that, because that rope has width to it, it's not really just a circle. What it is, in fact, is a little bit more like a coin, or what I'm going to call a disc. And that disc, the most technical term for it, is actually a cylinder. This cylinder has a height and it has a radius. What I can imagine is, instead of focusing on the volume of this entire region that I'm trying to trace out by revolving this entire region around the x-axis, I'm going to focus on the volume of one small disk that I will have traced out. And the volume for any cylinder is pi times its radius squared times the height. And what we're going to do is get this volume in terms of the function that we are looking at that defines this curve. And what that function represents, f of x itself, that is actually going to represent my radius. That distance from the x-axis up to the curve is just your y value. And the height of this disk, well, I've made it a really tiny sliver of this region. The width of it is just some very small change in x, which we will denote as dx, familiar notation that we've seen with both derivatives and integrals, which means the volume in terms of the function and the variables that I actually see in my graph would be pi times my function f of x squared dx. And now imagine that I could split this entire region into these very small representative rectangles. All would have their volume described the same exact way, and I would just want to add them all up from A to B. And the operation that adds them all up would be the integral from where the region starts to where the region ends of the volume for every individual disk. Because pi is a constant, I can remove it to the outside of this integral, And my final formula, what I'll end up with, is pi times the definite integral from a to b, the beginning and end of my region, of my function squared with respect to x. And so the real trick to this concept is that through revolution, you create a bunch of circles or disks and add their volumes together. And that'll do it for the intro to volumes of revolution. And I'll go a little bit more in depth into this process in the next video. Thank you for watching.